Welcome everyone to today's webinar. We're going to wait a few more minutes to give everyone a chance to join, and then we'll get started. While we're waiting, please note that this event is being recorded. The link will be available via email after the webinar has concluded. You won't be seen or heard, but if you're not comfortable with the recording, we invite you to sign off. In this session, we're going to talk about how we can use Spark to prove safety and security for embedded and system software. So what we hope is that you'll learn about what Spark is, a little bit about how Spark works, and then see how Spark can be applied using our M.A.R.S Rover as a demo platform, and we'll prove a safety property there. I'm Tony Aiello. I'm the head of product and innovation at Ada, and I'm also the product manager for Spark. So I'm really happy to be here today and to talk to you about Spark. If you have any questions during the presentation, please use the questions box. This is in the bottom right-hand side of your interface. These questions will be public, so anything that you ask, everybody will see. And then at the end of this webinar of my prepared presentation, we'll have an opportunity for questions and answer. Okay, so let's get started. Spark. Spark is deductive program verification. So when we talk about Spark, we're really talking about two things. First, an Ada-derived language that comprises both a functional specification language via subprograms and type contracts and an imperative programming language that's familiar, especially to folks who know Ada. Second, Spark is a tool that performs deductive verification. So the Spark tool takes Spark code, annotated with contracts, and extracts from this a set of logical formulas. We refer to these as verification conditions. And we then send these logical formulas to automatic theorem provers for proof. If you're familiar with SMT solvers, the automatic theorem provers we use are SMT solvers. We use 3, Altergo, Z3, and CBC5. So this is pretty cool because we're putting really heavy-hitting theorem provers in your hands, but allowing you to get access to them through a very high-level interface. So if all of the verification conditions are proved, what we know is that the program and its contracts are correct. So deductive formal verification. This may be an unfamiliar term for some folks on the call, so I want to give you a little bit more detail here. So with deductive formal verification, we're given preconditions, which is a set of constraints over the inputs to a subprogram, an implementation, how the subprogram works, and then the game is to prove that the post conditions, which are constraints on the outputs, are true based on these preconditions and implementation. So as a conceptual example, consider square roots. So we might write square root down as y equals square root of x. In this case, our precondition would be x must be greater than or equal to 0. Our implementation is going to be something complicated, so it's probably going to be based on Newton's method or some other sort of complicated way of computing a square root. But the post condition is very easy to write down. X should be equal to y times y. So this all assumes real numbers. And I like to use this as a conceptual example over the real numbers. If we were to actually look at this in a programming context, things get very complicated very fast because we have to deal with floating point imprecision and floating point boundary conditions, et cetera, et cetera. So that's not what we're going to do. Instead, to actually look at what deductive formal verification might appear like in code, I'm going to use a much simpler example. So here is an increment procedure. So this takes a single parameter x, which is both an input and an output, And we specified one precondition and one postcondition. So the precondition, x must be smaller than the largest integer, otherwise we can't increment it. And the postcondition is now stated very imprecisely. So all I'm going to promise with my increment procedure is that x is greater than x tick old, which means that at the conclusion of the subprogram, x is bigger than it was at the start of the subprogram. We implement this in the obvious way. X is assigned x plus 1, and Spark proves this with absolutely no difficulty. Right, so just a conceptual example. Of course, you would never actually write an increment procedure like this because that would be silly. And you would never write a postcondition that's this imprecise because, again, that would be silly. But I wanted to give just a flavor for what it looks like to write down a precondition and postcondition and illustrate how deductive formal verification works. Spark is both practical and modular. And it's modular. The practicality actually stems in part from the modularity. So when I say Spark is modular, what I mean is that Spark proves correctness one subprogram at a time. So I just illustrated how it proves the subprogram, but when one subprogram calls another subprogram, what Spark does is it assumes that the postcondition of the called subprogram is true, given that the precondition has been satisfied. And I'll show you in just a moment what that looks like. Now, there's a nice corollary to this. The corollary is that we have an escape hatch, if you will. We don't have to have Spark absolutely everywhere in our program. We can do foreign function interfacing. We could, for example, call out to C code. We could call out to Rust code. We could even call out to Ada code. And we could still say what we want to be true at the conclusion to that call. So you can imagine a C binding where we might have some preconditions. We might say it's only valid to call this C binding when these preconditions are satisfied. And we might have some postconditions. The C program will make these things true. We're not going to be able to prove that the C subprogram makes those things true because Spark doesn't analyze C, but Spark will then assume that C behaves correctly, and it will then be useful for the remainder of the proof that you're trying to do on your Spark code. The second corollary here is that subprograms can be used as lemmas. So if we want to encapsulate some piece of reasoning for reuse, all we have to do is put this inside of a subprogram, preconditions, postconditions, and now Spark can take that and apply it as a lemma. So for folks who are familiar with interactive theorem proving, this is the way we can bring in sort of the lemma-based process that you might be used to from interactive theorem proving and make it available in Spark. Option, definitely not something that's required. Spark is also practical. We can turn Spark on and off with subprogram granularity. And when we turn Spark off, effectively what we're doing is we're programming in Ada. So you can think a little bit like safe versus unsafe Rust, except of course Ada is safer than unsafe Rust. So you're maybe slightly better than in that analogy. This enables incremental or even partial adoption of Spark within existing code bases. I really want to emphasize the practicality here. Like, it would be great if all software everywhere were written in Spark and if it were all 100% Spark, but that's not practical. And so what we want to acknowledge is that there will be parts of your code base where you really want the power of Spark, and you can apply Spark there and then leave the rest of your code base as is. That's a totally legitimate way to use Spark. So modular verification. On the left-hand side, we have this increment procedure that I already talked through. And on the right-hand side, we have another procedure, use increment, which uses increment. So here we've introduced a counter variable, which we initialized to 0. And at the start of this procedure, what we do is we call increment. And so Spark is going to check, is the precondition for increment true? Well, it knows that counter is equal to 0. So yes, the precondition is true. Therefore, we can call increments. And Spark will assume the postcondition of increments, that x is greater than x tick old. So at this point, Spark knows that counter is greater than or equal to 0. Sorry, strictly greater than 0. It knows that counter is strictly greater than 0. But that's all it knows at this point, because that's all we've promised in the postcondition of increments. And this means that if we try to call increment again, the precondition check will fail. This is valid code, like we could actually run this and it would be fine, but Spark doesn't know that it's fine to do this because Spark's analysis is modular. We would have to strengthen the postcondition on increment, make it more precise in order to be able to call increment over and over and over again, as we've done here. So this just illustrates, again, you would never actually write code like this, and I acknowledge that, but this illustrates kind of two things. First of all, how the modular verification works. And second, it illustrates that sometimes you will prove a postcondition for a subprogram and find later in your code base that you need to increase the precision. There's a bit of a tension because you don't want to make a postcondition too precise. You definitely don't want to completely restate the functionality of the subprogram in its postcondition. This is not useful. You want to have some kind of a summary of what's going on, but it needs to be sufficiently precise to prove properties elsewhere in your code. Spark offers rich support for Ada constructs. So we have good coverage of core language features. We give you pointers via the ownership model that we essentially borrowed from Rust. We give you exceptions. You can both raise and handle exceptions precisely in your Spark code. We give you the ability to work with generics. So when a generic is instantiated, at that point, Spark will prove any of the contracts on the generic for the instantiated type. So it's very precise. And you can also do object-oriented programming in Spark via Liskov substitutability. This can get challenging. So, I think you should think carefully about whether you really need or want to use object-oriented programming, but we do offer that facility. Spark is a great language for embedded and systems programming, like I said. So tasking is available via the Jorvik profile, for example. We also have support for volatile. So if you need to talk to hardware, then you can tell Spark, hey, if I read this memory location, it's actually going to have some effect on hardware. And if I read it again, maybe it has a different value. So this is very powerful. If you're going out and talking to a sensor, for example, that uses memory mapped I/O, Spark can know that read after read after read could return different results. We also support functions with side effects. This is particularly useful for foreign function interfacing. So C, for example, often will return a status code in a function that's actually acting much more like an Ada procedure. It's doing some work, it's returning some things through its parameter list. And now in Spark, you have the ability to bind to that in a much more natural way than we asked you to do before. Finally here, Ada's representation clauses are fully supported in Spark, and that's great because representation clauses, I think, are one of Ada's really powerful features for embedded and systems programming. I always chuckle a bit when C programmers or Rust programmers talk about how good their language is for low-level stuff, and I'm like, but with Ada, you can get very precise about how you want to lay out the memory in your record. Spark's aware of that. It can reason about it. That can be part of your toolbox. Functional specification. Spark offers preconditions and postconditions, as we saw. You can talk about globals for data flow analysis. So if you want to be precise about what pieces of global state subprograms in your code base access, you can write that down and Spark will check it and make sure you're using those global variables in a manner consistent with what you specified. All of the features in Spark's formal specification are essentially first-order predicate logic. So you have access to quantifiers. Again, very powerful. You can also introduce ghost code. So if you need to be able to model some behavior in your software so that you can reason about it and prove, but you don't want to add to execution overhead, you can do this. You introduce ghost code. You can then very naturally introduce the modeling that you want. And then when you generate code, when you do the compilation at the end, that's what I mean by generate code. When you compile your Spark program, that code doesn't actually get emitted. It won't be executed. Finally, Spark offers support for termination. So you can approach full correctness, not just partial correctness, and termination is handled via proof. I mentioned just a moment ago the representation clauses, so I kind of want to lean into this. Spark gives you target-aware verification. So Spark's deductive program verification is based on the actual software that will execute. Spark has awareness of all of the machine-relevant details. It will match types between what you're doing in your source code and what's actually going to be happening on your targets. So machine integers, machine floats, we're not doing reals in Spark. We're not doing infinite integers. We're doing machine integers, we're doing machine floats. And as I said, if you have representation clauses that you've introduced for your records, Spark is aware of those. Finally, Spark has awareness of all of the runtime checks that are present in Ada, and it will use those to prove absence of runtime exceptions statically. So this makes Spark unique in the formal method space because you are able to reason precisely about the actual software that's going to execute on the actual target. Spark offers a couple of different levels of analysis. So on the left-hand side here, I'm sort of positioning Spark for cybersecurity. So Spark will prove memory safety. So this is very similar to what Rust has, where Rust is proving memory safety with its borrow checker. Spark is going to statically prove that your program is memory safe, provided you're fitting within that ownership model of Spark. Spark also has full awareness of the checks in Ada, and it will prove statically absence of runtime exceptions. So this means you're free from integer overflows, integer underflows, means you're free from array bounds, trying to access outside the bounds of an array. It means you're free from misuse of pointers. So many of the kinds of things that keep coming up as common weaknesses in the cybersecurity domain, Spark takes off the table with proof. And this is fairly automatic. And what I mean by automatic here is Spark already knows about all of these kinds of checks. So you don't have to ask for them. Spark is going to make these checks for you automatically. All of the memory safety checks, all of the runtime exception checks, Spark is going to make those for you automatically. You could stop there and you would already have sort of a very powerful story for cybersecurity and even for safety, because your software is not going to do unexpected things like raise a runtime exception that causes your guidance loop to shut down. You can also go further. You can go towards functional correctness, where you specify the behavior, develop an implementation, and then prove that your implementation satisfies that specification. This is what we just finished talking about when we talked about deductive formal verification. And there, you have to actually do the work to write the contracts. And as we'll see in a moment, you have to sometimes do a little bit of additional work to help Spark understand how to get from your implementation to be able to conclude that the contracts have been satisfied. Spark is wholly appropriate for systems and embedded programming because Spark is Ada. Spark is compilable by GNAT to fast, efficient, executable code, just like Ada. Spark is supported on every target supported by GNAT, again, just like Ada. So our native and host targets, Linux, Windows, and Mac OS through the FSF version of Spark. Architectures, we cover ARM, RISC-V, x86, PowerPC, Leon, 68K, pretty much any architecture you care about, we can target. Cross targets, bare metal, embedded Linux, Lynx OS, Pike OS, QNX, VxWorks, DOS, we've got you covered on targets. And we will also do custom targets. So if there's something that's not on this slide and you're like, gosh, I'd really like to use Spark, I wish it would run on, reach out to us. We'll be able to turn around a quote to you fairly quickly and tell you this is what it would take for us to get Spark up and running on your target. We do this all the time. Spark is also supported on all of our runtimes, including zero footprint. So if you want Spark to be in a really memory, computation constrained environment, we can support that through our zero footprint runtime. Spark Pro is industrial strength formal methods. So Spark Pro is our professional offering for Spark. We sell this via an annual subscription. It's professionally developed, maintained, and supported. We build it using Ada-Core's secure, reproducible build system, and we provide it to you open source with a warranty, with a software bill of materials, and we back it by our service level agreement. Spark has been qualified under EN 50128 and more recently under ISO 26262 to ASIL D. This is work we did with NVIDIA. So we can meet your needs on qualification as well. In terms of like getting up and running with Spark, if you're a little bit like, oh, deductive formal verification, that seems a bit scary, which frankly, it can be difficult to make that step. We offer mentorship with Spark. So this is dedicated training, dedicated consulting on your code that's designed to get you up and running in productive writing Spark. So at the end of mentorship, we want you to feel like you're empowered to move forward with Spark on your own, obviously relying on us with questions and any problems that you have using the technology. You always have that through our ticket system with our service level agreements, but we want to make you productive. We want to get you to the point where you're ready to use Spark. Spark offers strong IDE integrations. So here's an example of Spark running in VS Code. I kind of made this into an eye chart because I wanted to show you like, wow, look at all the features of VS Code that Spark plugs into. I'm going to do a live code in a moment, so you'll be able to see more of this. But what I really wanted to highlight is if there's a failed check, Spark will actually annotate your code right there in VS Code, so you can put your mouse over it and you can see what the message is that Spark is telling you about the code at that point. And again, I'll demo this in a moment when I do some live coding. Spark has current industrial users, so this isn't like cutting edge. It's cutting edge, it's very powerful, but this isn't technology that's not been used. Spark is proven in use. We have a lot of use cases up on our website. I encourage you to go and look at them. I've highlighted a few of these here. NVIDIA, we really like to talk about them because they've made such a strong adoption of Spark, both in their firmware team and in their Drive OS team. Latitude used this for like launcher development. We've got Welch Allen, JTECT. Again, I encourage you to check out the use cases, but the message here is Spark is real and it's supported, and there are folks out there that are using it today. All right, so with those preliminaries out of the way, I'd like to talk a bit about the Spark Rover. So this is a demo that we put together just this year for Embedded World, and I'm really excited about it because it's a cool new application of Spark on our side that, of course, we can talk about to customers such as yourself. So the Spark Rover is based on this M.A.R.S Rover platform. So this is a COTS kit. It has a Raspberry Pi Zero on it, and there is an Ada hardware abstraction layer that we wrote that allows us to interface with all of the hardware on this M.A.R.S Rover. Now, on top of this Ada hardware abstraction layer, we introduced another hardware abstraction layer, hardware abstraction layer, I guess, or a HAL abstraction layer. Anyway, so with this Spark HAL, we did two things. So the first thing we did is we provided a nice facade that allowed us to target our application of Spark to parts of the hardware abstraction layer that we were most concerned about. And then we proved absence of runtime exceptions. The other thing we did with this Spark hardware abstraction layer is we allowed the ability to swap out the Ada hardware abstraction layer and plug in a simulator that we wrote in Rust. So this is kind of a cool thing you can do in Ada, where you have a package and you can have two different bodies for the package. It's almost like inheritance in an object-oriented way if you're not familiar with it, except it's not inheritance. It's just like, hey, let me give you an alternate implementation of that interface, but without having to deal with all of the object-oriented machinery. So we can rip out the Ada HAL, we can plug in this Rust simulator, and then we can see how all of the code that we've developed works without having to have access to the hardware. And we've got blog posts that talk about these things. Again, you can find this on our blog. So with Spark, the other thing we did is we wrote a controller, an autonomous mode controller and a remote control mode. And for this controller, we proved a safety property. And that's what I'd like to dig into now. So I looked at this and I said, what would I like to prove for this rover? And I picked something that I thought was reasonably ambitious and also reasonably easy to talk about, which is, hey, we really should make sure that the rover won't crash into obstacles. So if I were to phrase this as a requirement, kind of putting on my requirements engineer hat, I might write it like this. The Spark rover shall not proceed straight forward, that is to say directly forward without turning its wheels, when the distance to an obstacle is less than some safety threshold. So let's assume that this requirement is validated. For example, we could have validated this as part of a model-based software engineering effort. So we would need to know things about vehicle dynamics, make sure we can stop in time, et cetera. Like there's a lot of kind of assumptions that underpin this requirement. But for the sake of this discussion, let's assume that all of those assumptions have been dealt with. And we know that this is a valid way of talking about safety for the rover. So in order to tie this requirement to the rover software, we'll pretty clearly need to have the ability to monitor things like the sonar distance and the driving mode, if you will, of the rover, which has three parts to it. It has the turn, how are the wheels turned right now? And it has the left and right motor powers, because we need to know whether or not we're going forward or going backward. So when we look at the hardware abstraction layer, we see that the hardware abstraction layer gives us setters. So here's an example. We have a procedure called set turn. We can pass into this a turn enumeration, basically, that says how we want the wheels to point. And then the hardware abstraction layer will go off, and it will make this true for our rover. We don't have a getter. So clearly, we're going to need to have some kind of a getter in order to formalize our safety property. Now, Spark gives us a couple of different options. One thing we could do is we could introduce ghost state to track the turn. So we could have some piece of global state that's marked ghost, which means that when we compile our code, it's not actually going to be in the final executable, but it's there for us to reason about with Spark. But if we did that, given that we have both the Ada and the Rust implementation, things would get kind of messy. So that's not the direction we picked. Instead, what we did is we introduced a model of a getter using an uninterpreted function. And I want to show you what that looks like. So what we've done here is we've written our getter. So, we should have some function called getTurn. It should return a turn kind. We're going to need to make sure the hardware abstraction layer has been initialized before we call it. So we introduce this precondition. And we're not actually going to implement this getter. So we mark it with import. Usually this would mean we're doing foreign function interfacing, but no, that's not what we're doing here. We're just saying to Spark, look, this thing is not actually going to be implemented anywhere. And oh, by the way, it's ghost. So we're never going to generate code for this. So now we have a getter. And the other thing that we've done is we have tied this getter to our setter using the setter's post condition. So the setter has a precondition. Can't call it unless the HAL has been initialized. And the post condition, the HAL is still initialized, right? So we want to make sure the setter doesn't somehow uninitialize the hardware, which if we didn't write down, Spark wouldn't know. But the second thing we've done here is we've said, when we run the setter, it will be the case that if we call the getter is going to return the turn that we put into the setter, right? So this is a way for us to basically tie the getter and the setter together. We're saying to Spark, look, this getter is going to behave like a getter should. So we're almost there. But this getter right now is a pure function. So it doesn't have any internal states that Spark knows about at the moment. And that means since there's no input, Spark is going to treat this getter like a constant, right? So Spark is going to see this pure function that has no inputs and say, well, if you call it, it's going to give you some value of turn kind. But if you call it again, it's going to give you the same thing because there's no reason to believe that it would give you a different answer on multiple calls. So what we need to do is we need to introduce a piece of abstract state, of ghost state, that represents how the rover's turning. And we bind the getter and setter together more tightly, if you will, with this abstract state. So this acts like a parameter that we pass into the getter that tells Spark, oh, look, when we called setTurn, that abstract state was written to. That means when we call getTurn, given that abstract state, we can get a different value out. So it's a little bit of an interesting detail. If you get it wrong, then you end up with unsound analysis. That's kind of unfortunate. But this is a thing that you need to be aware of when you're using uninterpreted functions. You have to write them down correctly so that they're going to behave the way you want in your modeling of the software. So now anywhere in our program, we can call getTurn, and this is going to give us the last value provided by setTurn, just as if we had actually implemented the getter, except we never wrote any code that's going to execute anywhere. So we take that same idea and we apply it to sonar distance and we apply it to the motor powers. You might ask yourself, why are you applying it to sonar distance? Isn't there just a thing you can query to get the sonar distance? But that thing you query to get sonar distance actually affects the state of the rover. And we don't want our model, we don't want our ghost code to affect the state of the rover. In fact, it can't. Spark won't let ghost code affect the state of actually executable code. So we have to introduce a getter for sonar distance, which we do. So with these pieces in place, we can now formalize the requirement. So I've replicated the requirement here. And now we can see cannot crash returns a Boolean. If the sonar distance is less than the safety distance and we're going straight, then it must be the case that we're going backwards. That's what this says. If we're violating our safety threshold and our wheels aren't turning, then we have to be moving backwards. The motor powers have to be negative. So that's the safety property that we've introduced. So with that, what I would like to do is pivot to doing a little bit of live coding. So I've never done this before. This is going to be an adventure. So let's see how it goes. So I'll turn off the screencast of the slides and I will share my VS Code window, which is right here. All right, so hopefully you can see my VS Code window. Hopefully this is legible. If not, then I apologize, but I did test it ahead of time, so I think it should be good. So this is VS Code, and we're running Spark. And so what I would like to do is I would like to show you how we're going to attach the safety property that we just discussed on the slides to the remote control mode for the rover. So I'm going to bring the safety property back just to show it to you. Here it is. Here's the safety property. This is the thing that I had baked onto the slide. I've got a little bit of additional information here. We need to have these preconditions and these globals in order for it to work. But all of these are related to the ghost state that I just mentioned when I was talking about modeling the hardware abstraction layer. Okay, so we have our run procedure. The run procedure is where we're going to implement the rover remote control. And so what we're going to do is we're going to introduce first a precondition for this. So we need the hardware to be initialized. So we'll start out by saying rover how.initialized, because we can't call our run procedure without initialized hardware. And then the other thing we're going to do is we're going to say that the rover, that we can't kick off the remote control mode if the rover is currently in an unsafe state. Now, this is a decision. We could actually imagine a remote control mode that lets a user drive the rover out of an unsafe state into a safe state. That would be more complicated, not what we're going to do today. We're going to assume that when the remote control mode is activated, the rover is currently safe. So that's our precondition. Now we'll add our postcondition. So we need to say again that we've not uninitialized the hardware abstraction layer, so we do that. And then the other thing we're going to say in our postcondition, of course, is that we're keeping the rover safe, so the rover cannot crash. So we've now written the contract for our run procedure. Now I will switch to the implementation of the run procedure and just really quickly kind of walk you through the logic here before we try and do any proof. So we got our run procedure. We've got some buttons. We've got a distance to our to any obstacle. We've got a current command and a last command. That's going to become really important in a moment. And then we've got some times because we want to be able to kick ourselves out of remote control mode. I'll explain that in a second. And then we have a variable to represent the state of our sonar mast. So we start out by setting the mast angle to 0. So we're looking straight ahead. And when we start our loop, what we're going to do is we're going to run this loop until basically nothing's happening. And this is because we were developing a demo for Embedded World, and we wanted people to be able to walk up to the rover while it was in autonomous mode, pick up the remote control, hit a button, have the rover switch over to remote control mode so the person can drive the rover around for a bit. But when they get bored and put the remote control down, we don't want the rover to just sit there. We want the rover to switch back to autonomous mode after a certain amount of time has passed. So that's what that's doing. So we poll for our buttons. We memorize the last command that we had, and then we check our sonar distance. And if the distance is less than our safety threshold, what we're going to do is we're going to say, basically, the user is not allowed to press the up button on the remote control. So this is how we're going to prevent ourselves from continuing to drive forward when the safety threshold has been violated. Otherwise, we'll do a little bit of maintenance, if you will, on the sonar. We'll look a little bit to the left and look a little bit to the right to make sure that there's not any obstacle off axis that we might be about to crash into. We're then going to take the buttons on the remote control and we're going to map these to a command. So really quickly, I'll show you what that looks like. So this function to command is implemented as an expression function. So we have an if ladder here. And all we're doing is saying, if the button is up and to the left, then we're going to go forward left. If it's up and to the right, we'll go forward right. And then we have our cardinal directions, and we have a kind of base case where the user's not asking for any command because no buttons are down. So I'll jump back here into our run procedure. So now, if the command is not equal to the last command, as in if the user is doing something different, then we're going to go out and we're going to talk to the rover. That's really important. We'll get to that in a moment. So if the command is forward, we're going to set the wheels to straight, and we're going to set the motor powers to positive. If the command is backwards, we're going to set the wheels to straight, but we're going to set the motor powers to negative. And this was one of the things that you saw when we looked at the safety property, that we were allowed to have wheels straight as long as the motor powers were negative, right? So I'll bring the safety property back and point to it. Wheels can be straight, but the motor powers have to be negative. That still is within our safety property. And then we have things like turning left, turning right, forward left, forward right, etc. So these are non-straight turns and motor powers that are set according to how we need to drive the rover. We have a base case here, which is this is the none case, which sets the motor power to 0. And then we wait for a second, or well, not a second, we wait for a fraction of a second before we go around the loop to give the rover time to actually move. Okay, so this is the whole implementation of run. I realize I went through it kind of quickly, but we're going to keep moving. So I'm going to click prove here. And basically I'm asking Spark now, hey, given the contract that I just established for you on run, can you show that it's true given the implementation? And while Spark's doing its analysis, I'll tell you look, it's done. I don't even have to tell you the answer. The answer is no, it's unable to prove the post condition just given what it has in front of it. So it says, oh, the post condition might fail. I cannot prove rover.cannot crash. And then it makes a suggestion. It says, this loop that's here in the body, it really should mention some details of the rover hardware abstraction layer. Why? Loops in Spark represent cut points in the analysis. So any variables that are assigned in the loop, Spark only knows what's true about those variables in the current iteration of the loop at the point at which the analysis sits. And at the end of the loop, when the loop exits, it only knows what was true. Sorry, it only knows what was established up until the point where we hit the exit statement that kicked you out of the loop. Otherwise, all Spark knows about variables that have been assigned in a loop is that they're consistent with their type. So we need to add information so that Spark can know what's going on in the loop. And we do this through a loop invariant. So let's do the following. We'll introduce a loop invariant. And in this loop invariant, we'll say, well, while this loop is running, we would really like it to be the case that the rover cannot crash, right? So we want to state our safety property and say throughout this loop, the rover cannot crash. So I'll do that, and then I'll kick off the analysis again. And while Spark is working, I will tell you, this is going to fail. Spark is not going to be able to prove this, but Spark will use this fact. It will assume that this is true after it tells me it's not. It will assume that this is true and say, but given that, I am able to prove your post condition, right? So it came back and it said, I can't prove this loop invariant. It might not be preserved by an arbitrary iteration. That does mean it's true the first time through a loop, so that's interesting. But it might not be preserved by an arbitrary iteration. However, it's not complaining about the post condition anymore, which means that this is a sufficiently strong loop invariant to guarantee our post condition. Not really surprising, it's a restatement of the post condition, but often this is a really useful way for you to do sort of debugging by proof or proof debugging. You can introduce facts upstream, see if those are true, and even if they're not, you can still see if those new facts were sufficiently strong to prove the property you're interested in. Okay, why is this not true? So this isn't obviously true because we have this statement here that's sort of memorizing the last command. So if the last command is equal to the current commands, then this if statement doesn't execute and Spark forgets everything it knows about what's going on. It forgets things about the turns, it forgets things about the power. So if the command was not forward, it's true that Spark set straight and it set left and right to negative, but it doesn't know that anymore because that was in the prior iteration. We didn't say anything about it in the loop invariant, and so it's forgotten. So our intuition here is that our code is correct. We know that if we're too close to an obstacle, we're not allowed to go forward because button up is false. And when we convert that to a command, that means we're not going to fall into the forward case, which means that if we're going straight, we're always going to be negative, but we haven't written that down for Spark. So what we're going to do now is we're going to write that down for Spark. And I'm running a little bit short on time here, so I'm just going to copy paste this thing and then kind of talk you through it. So this is the intuition that we just walked through. So if the command is not equal to forward, then we either are not going straight or the motor powers are negative, okay? And this property is enough for us to prove the loop invariant, rover.cannot crash, and it's therefore enough to prove the post condition, rover.cannot crash. So this is an example of how sometimes you as the programmer need to add a little bit of information, especially within a loop, to help Spark be able to see that a critical property like rover.cannot crash is true. It seems probably a little bit magical here because I'm talking fast, I'm moving through code that's unfamiliar to you, but what I want you to take away from this is normally this would be code that you wrote, and therefore you would have all the intuition already in mind for why these things should be true. And so it would be more natural for you to say, oh, well, I think this is true because, and write that down as a loop invariant, and then have Spark tell you, yeah, that really is true. And moreover, that's enough to prove the property you're interested in. This is also why we have mentorship, because it helps you start to think in these ways. And at the end of the day, you always, as a supported customer, can open a ticket and say, hey, I'm really struggling with the intuition here. What am I missing? What might be a loop invariant I need? And we'll definitely help you with that. All right, that was my probably very rapid fire live coding. So now I'm going to switch back to my slides and we're going to wrap up here. Ooh, yuck. What did this do? Sorry, let me see if I can fix this funny letterboxing. Slideshow. No. All right, well, don't know what's up with the letterboxes, so we're just going to leave it like it is, and we're going to keep going. So I showed you proof of remote control mode. Wasn't entirely automatic. It required a little bit of reasoning about the prior commanded value, and we had to carry that information around the loop through a loop invariant. There was actually more work that was done here that I didn't talk about today because I don't have time, but if you're interested in seeing sort of the more work that was done, we actually found something that looks a little bit like a bug if you squinted at it, actually an implicit assumption that could have left the rover in an unsafe state depending on reuse. You can go to the blog post, there's a link here, and then at the end of the webinar, you'll actually be redirected to the blog, so you'll have an opportunity. Oh, look. Karis just popped something up here so that you can see. If you're interested, you can go to my blog and you can read more about it. It's great. I wrote it. You'll love it. I promise. Okay, I want to say one more thing before I wrap and take questions. And I apologize if this is getting a little bit long. I want to talk just for a moment about Spark and generative AI. So there's been a lot of hype around generative AI. I'm sure that's not surprising for anybody on the call. My position, if generative AI is the future, Spark is the best possible language to use. Why? Because Spark provides deductive formal specification, as we've just been talking about. Sorry, that should actually say provides deductive formal verification. It's like the third time I've presented this and I didn't see it. I apologize. Spark provides deductive formal verification. The specifications for Spark are easy to read and they're easy to understand. So you could write down, or you could be given a formal specification for a subprogram that might be very complicated, convince yourself it's correct. And then because of Spark's work, you would be able to say, oh, it doesn't matter, at least to a first approximation, what the generative AI does to implement that code, as long as I can use Spark to prove that that implementation matches its specification. Of course, Spark compiles to efficient executable code. It's qualified. We commercially support it, and it supports a large number of target platforms. So right now, what we're doing is we're working on ways to improve the use of Spark with generative AI. Come find me later. You can definitely send me email. We may run out of time in the questions, for which I'll apologize in advance. But I'd be happy to talk about things that we are doing right now to make Spark work better with generative AI. Our next webinar, shameless plug, my colleague, Stephen Hedrick, is going to be presenting a webinar on the 8th of July, Tuesday, the 8th of July, called Navigating Mars with Rust. So I definitely encourage you to check that out if you're interested in Rust, if you're interested in more things around this Mars rover concept. This will be a really great webinar. And then the other thing I want to leave you with, and I'll kind of leave this up as I take questions, we've got a couple of tech days coming up. So the first one is in Denver, and that tech day is in September. The second one is in Munich. That's in October, but please notice the sign-up date for Munich is before the sign-up date for Denver. So if you're interested in going to Munich, don't wait. Sign up now, because you only have until the 30th of June to do that. Okay, I will now move through questions, and I don't know the order in which these were asked, so I'm just going to start at the top. Does Spark support features from Ada 22x? Yes, anything that Gannat supports in 22x, Spark supports in 22x. That's the simple answer. If you've got a particular feature that you're interested in knowing more about, I invite you to send mail to me or send mail to info@adacore.com. We'd be happy to reach out to you and let you know about that. So Samuel asks, why exceptions are back in Spark when there's proof of absence of runtime exceptions? So these are user exceptions. That's a really good question. Thank you for asking it. Runtime exceptions are things that kind of come from the language, come from the runtime itself, as it's doing checks for things like array access or doing checks for things like integer overflow or underflow. With Spark's exceptions, we're not talking about those. We're talking about user exceptions. So if you want to raise an exception and then handle it elsewhere, Spark gives you a precise way to talk about what you can depend upon in your handler when that exception has been raised. So that's why that's there. Mattia asks, would it make sense to write formal software requirements using Spark? Yes and no. So yes, it makes sense in that first order predicate logic is generally a good logic in which to write formal software requirements. No, because you'll leave a lot of the value on the table if you don't then also develop your implementation in Spark. The other thing I'll say here is that formal systems that are really focused on just software specification often give you ways to do validation. They'll give you like a simulation capability or some kind of a visualization capability that you can use for validation of these specifications. You can do this with Spark. It's not really what Spark was designed for, so it may not be the best fit. So I would encourage you to absolutely use formal systems to specify your software. I would absolutely encourage you to use Spark, but I think that unless you're planning on doing your implementation in Spark as well, you're probably leaving a lot of the real value on the table. Raphael asks, what kind of feedback did you receive from developers and companies that have recently adopted Spark in their projects? In general, people like Spark. We've got some people who struggle with Spark. We've got some people who don't like Spark. This is somewhat normal, I think. A lot depends upon the precise details of the code to which people are applying Spark. So some of the people who dislike Spark the most that I've talked to recently are trying to interface with it, for example, with a C++ library or a C library that does very complicated things with memory. And it becomes very complicated to express all of that in a way that Spark understands, that allows you to reason about it. This can be a challenge. So if you're thinking about adopting Spark, if you have some use cases in mind, I would definitely invite you to reach out to us, info@adacore.com, and say, hey, I'd like to have a discussion around Spark, tell you a little bit about what I'm thinking, how well is that going to work? We're not going to tell you no, right? We're going to help you find a way to use Spark as effectively as possible in your development workflow. Andreas asks, is it possible to use one zone SMT solver? Yes-ish. So Spark uses Y3 as part of its underlying infrastructure implementation. And if there is a Y3 driver for your SMT solver, then you would be able to bring your SMT solver into Spark. How well that's going to work is perhaps an open question. Again, if you're interested in exploring this, I invite you to reach out to us. Andreas also asked, which SMT solvers do you use? Alt-Ergo, Z3, CVC5. These are the three SMT solvers that we package with Spark today and enable by default. We also have Calibri in the mix. Calibri is an SMT solver that's designed for nonlinear arithmetic. You can activate Calibri, not activated by default, but it is certainly shipped with Spark. And it looks like we've got a couple more questions, so I'll take those. Kevin asks, are you developing or tuning an LLM to specialize at Spark generation? No. Will you release a product like this? So what we're actually doing at the moment is we're experimenting with MCP, the Model Context Protocol. So what we have found over the last couple of years is that the foundation models are getting better so fast that anything we would be able to do would not be able to keep up. Today, I've had anecdotal good experiences with Claude Code and Spark. For example, I gave it a correct implementation of bubble sort that did not have any loop invariants in it at all. And I asked Claude Code to to prove the bubble sort. And I gave it an MCP that had a little help feature so that it could, get a little bit of help if it got stuck on loops, for example. And Claude Code was able to complete this proof fully automatically. Like all I typed in at the Claude Code prompt was, I want to prove this code, enter. And about 4 minutes later, I had a completely proved implementation of bubble sort. So that's the kind of thing we're working on right now. And I think that's what you should expect from us going forward. Fine tuning is too costly and too slow. That's our current feeling about this. Samuel asks, would you be able to describe why in some cases it's more convenient to employ proof and why in some cases it's easier to test software? Ooh, that's a really good question. Let me try to pull some thoughts together. So an advantage in proof is you don't have to build a test harness. So if I have a subprogram and it has a contract on it, I don't have to write a test harness. I don't have to generate values to send into it. And I don't have to build something to check the values that come out of it against my Oracle. The Oracle in some sense is the post condition, and the preconditions in some sense, they bound the test cases, but I don't actually have to do any of that machinery. All I have to do is click prove, as you saw when I was running VS Code a moment ago. So that definitely makes it easier to prove software than test software. I also don't have to have access to my targets. I don't even have to have fully compiling code yet, right? All I have to do is be able to get that unit to compile, and the closure of dependencies, I guess, around that unit that are used for that subprogram. And then I can click prove and I can get some feedback on that. So that's a case where it's definitely more convenient to employ proof. There are certain kinds of properties that can't be stated comfortably in first order predicate logic. I mean, of course, there are properties that can't be stated at all, but unlikely to hit those in common software development. But there are things like temporal properties are uncomfortable to state in first order predicate logic. Maybe it would be easier to develop a test harness to look at temporal properties. In other cases, you may just have properties that are so complex, but also the code itself is so easy to read and understand and convince yourself that it's right, that you would rather test it. Have some kind of a rigorous testing approach that you take. You're not going to do full combinatorial testing. That's always going to be off the table, I think, for anything of reasonable complexity. But you may be able to do MCDC testing, and it may not be worth the effort to try to fight with the proof system in those cases. Like concrete examples are really hard to give, but I think this is maybe some intuition that would allow you to say like, oh, I would just review this code very carefully and also test the heck out of it according to my process, rather than try to bash my head against the proof system, because I've got like triply nested quantifiers or something, which are probably going to eat the SMT solvers. I hope that's a good answer. If you want to talk more about that, feel free to reach out by email and we can continue the discussion. Son asks, do you envision a better link between formal specification languages and Spark? Speaking for Ada Core, no, but some of our partners are looking at this. It's a great question, and it's definitely a rich area. This is something that we certainly could look at in the future. This is something that if you as a customer are really interested in, especially if you're already using formal specification and you would like some guidance on how to build a bridge between that formal specification and what is done in Spark, we would be delighted to talk to you about it. But in terms of bringing a product to market that explicitly addresses what you're talking about today, that's not on our roadmap. And to give you a little bit of intuition as to why not, that really begins to push hard into software development methodology. And what we want is to be able to position Spark as a tool that can work today in a kind of methodological agnostic way. So it doesn't matter if you're using formal specification with such and such language. It doesn't matter if you want to convert all of your software or only a part of your software to Spark. Spark is still going to deliver value for you, and that's where we're starting today. Hopefully that makes sense. Again, if you want to dig on this topic some more, feel free to reach out to me by email. Okay, oh, there's a new question hiding above here. Let me scroll up. Okay, so Andreas asked about the link to my blog, which Karis reshared. Thank you, Karis. So hopefully you have that. You can also find the blog just by going to adacore.com and then clicking on blog. And I don't know, you'll have to scroll a bit. I guess that's a bit awkward, but certainly it's on there. All right, while I wait to see if there's any final questions, I'll kind of start my wrap up here. Again, our next webinar is going to be Rust, M.A.R.S Rover. So please, I encourage you to come and see that. If you're at all Rust curious, you can hear a bit about what we're doing in Rust. And if you want to learn more about Spark, if you want to talk to us, if you want to see what Ada-core is doing with all the rest of our tools, I really invite you to come to one of the 2 tech days that I mentioned that are up on the screen here. We've got our Munich Tech Day in October, but registration closes in June. And we've got our Denver Tech Day in September. For that, registration closes in July. If you want more information about our events, you can go to adacore.com/events and you can see our whole calendar. So I encourage you to take a look at that. And seeing no other questions, I will say thank you everyone for attending. Please don't hesitate to reach out by email. We'd be delighted to talk to you. And thank you. Have a good rest of your day.